Hello everyone. In this video I'm going to explain the design of shell and tube heat exchanger. As we all know that there are many types of heat exchanger like double pipe, shell and tube, plate and frame, spiral, coil heat exchanger. So in this video we'll be going through shell and tube heat exchanger and Kern method, that is a well-known method for design of shell and tube heat exchanger. It is basically an iterative procedure. Initially we assume the value of overall heat transfer coefficient, and then we go through a number of steps to verify if it is close to the calculated value of overall heat transfer coefficient. So iterations continue, and when difference becomes less than or equal to 10%, then it is okay. We can use that design as final. So first step is determination of heat duty, so which is Q is equal to mCp delta T. We need flow rate, specific heat capacity and temperature difference, so we can easily determine this value of overall heat duty. Then based on the heat duty we can find the mass flow rate of cooling water or utility or process stream required. So here mass flow rate of cooling water can be determined using the heat duty, specific heat capacity and temperature difference. Then we need to list down all of the physical properties including the specific heat capacity, density, thermal conductivity and viscosity based on the mean temperature. Like if hot stream temperature is 400 at inlet and our outlet is as 300, so we can take the physical properties at 350 degrees Celsius. Similarly, for cold stream, we need to calculate all of the physical properties at mean temperature. So you can either go through the empirical correlations to calculate these physical properties, or you can use S1 ICs or similar softwares to calculate the physical properties. So here I have written down all of the physical properties. Then you need to estimate the overall heat transfer coefficient. That is initial assumption. So based on the calculated guess we can use the figure 1, this figure, like you can see from here, shell and tube heat exchanger, and then hot fluid and cold fluid are listed, and then here we have overall heat transfer coefficient, so we can take any value between these and then we can perform the iterations to calculate the overall heat transfer coefficient. So I have taken here as 70 degrees 70 watt per meter square per degree C as overall heat transfer coefficient. So next step is to calculate the log mean temperature difference. So here we have log mean temperature difference. So we can substitute the values to get the log mean temperature difference as 57.37 Kelvin. Then we need to calculate the temperature correction factor. We all know that streams are not counter current. There is not an ideal process where we have 100% counter current or co-current streams. There is some other non-idealities involved which are encountered using this temperature correction factor. So this is the equation for temperature correction factor. Here R and S are two parameters that are totally dependent upon the temperatures of hot and cold stream. So using these values we can determine R and S values here, and then after substituting the values in this FT factor we can calculate it as 0.908. So as long as this value FT value is greater than 0.75, it is acceptable. If it goes below this value, then we need to change the orientations, or we can use two heat exchangers in series or parallels. We need to change the arrangement. Okay, so then we need to calculate the mean temperature difference, which is basically this correction factor multiplied by log mean temperature difference. So finally we obtain the mean temperature as 52.08 Kelvin. Then we need to calculate the heat transfer coefficient area required, which is basically Q is equal to UA delta T. So rearranging we can get the overall heat transfer area. So we obtained it as 227.01 meter square. Then we need to finalize the tube layout and tube sizes, and we need to specify which stream will be on shell side and which stream will be on tube side. So here we have taken the flue gas stream on the shell side and cooling water on tube side. uh, there are many justifications available for assigning tube and shell side. You can go through the details through the chemical engineering design by CNET volume 6, Richardson Coulson. So, and then I have assigned here one shell and 8 tube pass heat exchanger, and tube outside diameter is taken as 38 mm and inside diameter is 32.8, and effective length is 6.1. You need to take these values from standards, and then triangular pitch is used. So based on the overall heat transfer coefficient area and single tube heat area, we can determine the number of tubes, which is determined as 312. Then we need to calculate the tube velocity in order to check whether it is under the limit or not. So it is a bit low compared to the limits. It should be close to 1 meter per second. For water case, it can be around 2 meter per second. Then we need to calculate the shell bundle shell and bundle and shell diameter. So for that we have this correlation, uh, which is basically dependent upon the number of tubes and tube outside diameter, and here we have two constants which depend upon the orientations. So based on the selected number of tube and shell passes, we can have these constants k1 and n1. So using these constants we can determine these values, value of bundle diameter, which is 1.121 meter. Then we need to specify the clearance between the bundle diameter and shell diameter. So based on the type of heat exchanger, we can calculate the clearance from here. Like if bundle diameter we previously determined, based on the different types of heat exchanger, we can calculate the clearance. So after adding the clearance here in the bundle diameter, we can calculate the shell diameter, which comes out to be 1.197 meter. Then there is another check, like length over diameter, shell diameter ratio should be between 5 to 10. So it is acceptable in this case. Then we need to calculate the tube side heat transfer coefficient, which depends upon the Reynolds number and Prandtl number. So we can calculate these Reynolds number and Prandtl number using the relations, and then we need this L by D ratio. Uh, so it is 141. So now we need to go to this equation, this figure, to calculate the JH factor. So here we have Reynolds number. Based on the Reynolds number and L by D ratio, we can easily calculate this heat transfer factor. Okay, so then we need to calculate the tube side heat transfer coefficient, which is given by this equation. So we previously determined JH, Reynolds number, Prandtl number, and these two are basically parameters like thermal conductivity and inside diameter. And this is viscosity correction, we can neglect that, and after substituting these values we can calculate the tube side heat transfer coefficient as 1412.62 watt per meter square into degree Celsius. Then we need to evaluate the shell side heat transfer coefficient, and for that we need to calculate the equivalent diameter for shell side, which basically depends upon the tube pitch and tube outside diameter, and we have two different pitches like triangle and square pitch. So first of all we need to determine the pitch, which is 1.5 times outside diameter. Then after substituting these values, since we already selected the triangular pitch, so we will be using this equation, so we can calculate the shell side equivalent diameter. Then we need to calculate the baffle spacing, which is 0.3 to 0.5 times the shell diameter. So we have taken as 0.4 value, so we can calculate this baffle spacing. Then we need to move forward to calculate the area for cross flow. So we have pretty much all of these parameters like tube pitch, tube outside diameter, shell diameter, and baffle spacing. So after substituting these values, we can calculate the value of AS. Then we need to calculate the shell side mass velocity. So this is flow rate. It is divided by this area which we determined in previous step. So we can easily calculate this GS value. Then we need to calculate US velocity, which is shell side velocity, and then Reynolds number and Prandtl number. So after we are done with the Reynolds number, we can calculate the GH value for shell side using the baffle cut, which can be anywhere between 15 to 45. So from where we can determine GH value. So after we are done with this GH value, we can calculate the value for shell side heat transfer coefficient. Since we have everything like GH factor, Reynolds number, Prandtl number, thermal conductivity, and this equivalent diameter, and this is neglected for this case. So we calculate the shell side heat transfer coefficient as 74.35 watt per meter square into degree Celsius. Then we need to move forward towards the overall heat transfer coefficient, which is given by this equation. And here we need to calculate the fouling. We need to take the fouling factor for shell side and tube side, which can be taken as 5000 for both sides. After substituting these values, we obtain the value of overall heat transfer coefficient as 71.85, which is pretty much close to the assumed value of 70, and error is very small, so it is okay, we are good to go. Then we need to evaluate the tube side pressure drop. Here we have tube passes, and we have JF factor. So again we need to find the JF factor using this figure. Based on the Reynolds number, we can easily calculate this JF factor. So then we have everything like density, tube side velocity. So after substituting these values, we can easily calculate the value of tube side pressure drop. Then we need to finally calculate the shell side pressure drop. So again we need JF factor. So based on the Reynolds number, we can calculate the JF factor, and again we can select the baffle cut anywhere between this, but make sure we keep the baffle cut same for both heat transfer and thermodynamic for hydrodynamic calculations. So we calculate the value of JF, and after substituting these values, we can calculate the value of shell side shell side pressure drop. Okay, thank you. That's all for this video. See you soon.